So I will talk about simulation of near Clifford circuits on a noisy quantum hardware. And let me start this basic question. What is the cost of simulating a quantum circuit on a given hardware? We can measure the cost in terms of the runtime or energy consumption or something like that. And a small circuit with 20 or 30 qubits can be easily simulated on a classical computer. To simulate larger circuits, we might have to use quantum hardware, say superconducting qubits, ion traps, and so forth. But of course, quantum hardware is noisy, so we have to make our circuit fault tolerant. And error correction is the only known solution of fault tolerance. But as you know, it is expensive. There is large qubit overhead, and error rates must be below error correction threshold. And error mitigation is an alternative to error correction. It has very bad asymptotic scaling, as I illustrate on this plot. In fact, asymptotically, error mitigation is much worse than classical simulation. But we expect that there is a regime of intermediate circuit complexity, then error mitigation is the most cost-effective solution of the fault tolerance problem. As you know, error correction converts physical operations, which can be noisy, to logical operations acting on encoded qubits, which are protected from noise. In contrast, error mitigation does not improve gate fidelity or qubit coherence time. It works by repeating a noisy quantum circuit many times and processing outputs of these circuits in a way that cancels the contribution of noise. And each method has some pros and cons, as you can see in this table. Let me just say that error mitigation is more flexible in terms of what gate sets we can simulate. It does not require many ancilla qubits, but we can do error mitigation only on a certain special class of quantum algorithms that measure expected values of observables. For example, variational quantum simulators. Today I will discuss ideas how to combine error correction and mitigation to address the shortcomings. And for the first part, we shall consider logical T-gates and error mitigation applied to logical qubits. And the second part is about Coherent Pauli checks, which is a previously known error mitigation method. And in fact, Ken Brown is one of the inventors behind this idea. And I will describe a simple theory that we can use to prove rigorous performance guarantees. And I will also show you some experimental results. If we talk about error correction based on topological codes, such as the surface code, some logical gates are easier to implement than others. Logical Clifford gates, such as Hadamard, CNOT, and S-gate, can be introduced only small overhead because we can implement them either transversally or by code deformation method, like braiding defects in the surface code. But to achieve universality, we need at least one non-Clifford gate, such as T-gate. And realizing T-gate fault tolerantly requires complicated methods like the magic state distillation or increasing a special dimension of the code. And this can be expensive. So this picture that I borrowed from the paper by Fowler, David, and Jones gives you some idea how expensive it could be. And this brings me to our proposal. So here we are trying to take the best of the two worlds. We use error correction to realize high fidelity logical Clifford gates. And then we apply error mitigation at the logical level to realize high fidelity T gates, logical T gates. And this removes the need for magic state distillation. And we estimate that for realistic error rates, we can implement circuits with about 10,000 logical T gates. And this regime is already hard for classical simulators. But the drawback is that error mitigation comes with a large overhead. So we would have to repeat the circuit many times. And error mitigation only applies to expected values of observables, so we cannot simulate single shot measurements. And first, let me try to explain how we implement this proposal. And first, I will give you some background on error mitigation. And our main tool is the quasi-probability method introduced by Pashayan, Volmont, and Bartlett. Suppose our goal is to estimate expected value of some observable O on the output state of some quantum circuit U. And we have some set of available operations, which I denote E sub I. And these are operations that we can implement on our hardware. For example, E sub I could be a noisy quantum circuit. And you should think of each operation as a map or quantum channel that maps density matrices to density matrices. And we can try to express the desired operation U, our ideal circuit, as a linear combination of available operations with some coefficients. And we call this a quasi-probability decomposition because some of these coefficients in the sum can be both positive and negative. So they are not necessarily probabilities. And then by linearity principle, the desired expected value becomes a linear combination of things that we can measure on hardware by implementing each of these operations E sub I and measuring the observable O. But in all interesting cases, the number of terms in the sum is exponentially large. So we cannot examine all the terms. What we can do is to estimate the sum by Monte Carlo method. So we randomly sample a small subset of operations E sub I, and the probability of picking some E sub I should be proportional to the magnitude of corresponding coefficient. And the number of terms that we have to sample is controlled by this parameter gamma, which we call the negativity. And you can think of this as normalization of our quasi-probability distribution. So if we want to approximate the desired expected value with some error delta, the number of samples scales like negativity squared divided by delta squared. So this method is only practical if the negativity is small. And now let's apply this to logical operations encoded by some stabilizer type quantum code, say the surface code. And now all operations are defined at the logical level. And our desired operation is logical T gate, and available operations are shown here. We can initialize a qubit in 0 state. We can apply any Clifford gate. We can measure qubit in the standard basis. And in addition, we can initialize a qubit in some mixed state rho, which is close to the magic state defined in this yellow box. And as I said before, all these operations are relatively easy to implement for example, by braiding defects in the surface code. So it is likely that the first error-corrected quantum processors will support all these operations. And our error mitigation protocol consists of 3 steps. First, we use this standard gadget that converts a noisy magic state to a noisy T-gate. And this gadget requires only Clifford operations. And it implements ideal T-gate followed by a certain noise channel. And this noise channel applies Pauli Z error with some probability epsilon t, which is simply related to fidelity of our magic state. Then the second step is to learn the noise channel. And what we propose is essentially a randomized benchmarking. We initialize a qubit in the X basis, then we apply noisy T-gate several times to amplify the effect of noise. And finally, we measure the qubit in the X basis. And we can choose the number of repetitions such that the T-gates cancel each other, and we just measure the noise. So then we can fit the exponential decay of the measured signal and estimate the T-gate error rate with a small relative error. And once we know the error rate, we can express our ideal T-gate as a linear combination of the noisy T-gate and noisy T-gate followed by Pauli Z error. And the coefficients C1 and C2 are simple functions of the error rate, which we already know. And the sampling overhead is controlled by the negativity, which is given by this formula. So to minimize sampling overhead, it is crucial that we make this negativity as small, as close to 1 as possible. And for that, we need a protocol for preparing high fidelity logical magic states. And fortunately, this has been already done. So in the case of the surface code, such protocol was proposed in this paper by Ying Li, titled Magic State Fidelity Can Be Superior to Operations That Created It. And the paper considers a circuit-based noise model. So physical CNOTs have some error rate P CNOT, and single qubit gates have some error rate P1, which is much smaller than P CNOT. And this is a reasonable assumption, at least in the case of superconducting qubits. And this paper shows that one can prepare a logical magic state encoded by the surface code with the error rate roughly 2/3 times P CNOT. And this constant coefficient 2/5 does not depend on the code distance as long as the distance is large enough. And now we can estimate the sampling overhead of the quasi-probability method just by plugging this expression into the formula for the negativity. So let me just show you the final answer. So suppose our goal is to simulate a Clifford+T circuit. And this circuit contains some number of T gates, which I denote N sub T. And we have 2 options. We can either do the simulation on a classical computer, or we can use a quantum hardware with logical qubits encoded by the surface code. And because magic state distillation requires too many logical qubits, let's say that instead we want to implement logical T gates by the quasi-probability method that I showed you. So in both cases, the simulation cost scales exponentially with the number of T gates. And so the best known classical simulators based on the Gottesman-Neal theorem and its generalization can simulate about 50 T gates. But if you go to 100 T gates or more, this exponential scaling kicks in and simulation becomes completely impractical. But in the quantum case, the exponential scaling is sufficiently mild that we can simulate about 10,000 T gates, assuming that physical CNOT gates have error rate about 0.1%. And you can also think of this example as a polynomial quantum speedup. The degree of the polynomial is very large. And of course, this is oversimplified picture because I completely ignored all factors in front of the exponential scaling that depend on the number of qubits, number of Clifford gates, and so on. But this is sort of consistent with the plot that I showed you in the beginning. So this is all I have to say about logical T gates. And now I want to change the topic and talk about Pauli checks. Sorry, my voice. My voice is not good. Yes, again, let me start with a motivation. What we would like to do is to extend error mitigation to single shot measurements. In the first part, I only considered expected value measurements. This means that the output of a quantum circuit is only used to estimate expected values of some observable, say, Pauli operator. And such measurements are often used in variational quantum algorithms. But most of textbook algorithms like Shor's factoring or quantum phase estimation require single shot measurements. This means that each time we implement the circuit, we want to get a sample from the output probability distribution. And almost all error mitigation methods apply only to expected value measurements. And this is a shortcoming that we would like to address. Now, our approach works only for circuits that are dominated by Clifford gates. And for concreteness, let's assume that the circuit looks like shown here. So we have 2 layers of single qubit gates on the left and on the right. And in the middle, we have arbitrary Clifford circuit. And the task is to sample output distribution of this circuit. This task becomes classically hard already for 50 or 60 qubits. In fact, such circuits were proposed as candidates for demonstrating quantum advantage in this paper by Adam Bulland and others. I will focus on mitigating errors in the Clifford layer because it contains it potentially contains large number of CNOT gates, which are the most noisy gates. It is known that CNOT cost of a Clifford operator on n qubits can be of order n squared in the worst case. So if n equals 50, we are talking about a few thousand of CNOT gates. And I will make a simplifying assumption that these single qubit gates are noiseless. Okay, so and the main idea is to detect errors by verifying circuit identities which are satisfied in the ideal case. So the identity shown here says that any Pauli operator L on the left side of a Clifford circuit can be cancelled by applying a suitable Pauli operator R on the right side. And this is just another way of saying that conjugating a Pauli operator by a Clifford gives another Pauli. Now, if we consider a noisy case, this identity is satisfied up to a sign ±1. And this sign is analogous to error syndrome in error correction. So it depends on whether the error operator commutes or anti-commutes with Pauli check operators. Now, there are many different ways we can introduce an error in a quantum circuit. But if all errors are Pauli type and the circuit is Clifford, we can commute all errors towards the left and merge them into a single Pauli operator. And this is what I have done here. And then the syndrome controls whether the error commutes or anti-commutes with the left check. And now we can measure error syndrome by bringing in one ancillary qubit that controls application of our Pauli checks. And this payload circuit U in the middle is just the Clifford part of our target circuit that we want to implement. And I'm ignoring layers of single qubit gates on the left and on the right because we assume that we are ideal. And I'm going to pick the left Pauli check uniformly at random from the n-qubit Pauli group. Then no matter what errors happens in the payload circuit, the probability that the error anti-commutes with the left check is exactly 1/2. It means that we can detect 50% of all errors in the payload circuit. On the other hand, the overhead introduced by this Pauli check is relatively small. We need just one extra qubit, and we need about n extra CNOT gates to implement these controlled L and controlled R operations. And this idea is not new. So here I show some references. And most of constructions that we use here were introduced by Ken Brown and Debroy in this paper. So in general, we can apply several Pauli checks sequentially. And at the end of the day, we post-select zero syndrome on every check. So if errors happen only inside payload circuit, the probability of detecting this error would approach 100% as we increase the number of Pauli checks. But of course, errors happen everywhere, including Pauli checks themselves. And the worst case scenario is when an error happens in some of outer Pauli checks, like L1 or R1. Such errors are undetectable, but they can potentially damage data register. On the other hand, if an error happens in some of the inner Pauli checks, like L3 or R3, such errors are likely to be detected by the outer checks. So such errors are less dangerous. And this means that we should expect a sort of a catalytic effect. As we keep adding more and more Pauli checks, the effective noise strength should decrease exponentially because errors in the inner checks are likely to be detected by errors in the outer checks. And if our error rate is small enough that we can reliably implement just a few outer checks, we should be able to implement the entire circuit reliably, no matter how many gates are in the payload circuit. And we can actually prove this catalytic effect and quantify it, and I will show you this in a moment. And this is a brief history of the Pauli check idea, and it goes back to this science paper by Brun, Devetak, and Sheikh. And the focus of this paper was quantum communication theory. It was shown that a small amount of entanglement shared between the sender and the receiver enables reliable transmission of a very large number of qubits. And here we exploit a similar catalytic effect in the context of error mitigation. So then 10 years later, Chancellor and Rofi and other people introduced a notion of coherent parity check. And they showed that this is a fruitful way of thinking about quantum codes. And these coherent parity checks are essentially identical to Pauli checks that we use here. And as I already said, this idea was brought into the context of error mitigation by Ken Brown and Ken's Colfer. And more recently, it was rediscovered by Gonzalez, Shayudulin, and others. Okay, so let me briefly sketch the theory behind Pauli checks. So here I show the main quantities that we would like to compute. Error mitigation results in a logical error if we observe zero syndrome on every check, but the payload circuit contains some non-identity error. This is a logical error. And of course, we want to make the probability of logical error as small as possible. And post-selection probability is how often we actually measure zero syndrome on every check. It controls the sampling overhead. And I will consider a circuit-based noise model. So we have some physical error rate epsilon, which is basically the error rate of CNOT gates. In the first part, I denoted with P CNOT. So sorry, I'm not using consistent notations. And we allow errors everywhere, both in the payload circuit and in the Pauli checks, and assume that single qubit operations are ideal. So suppose we have already implemented some number of these Pauli checks. Then we shall end up in one of the following three states. State one means that at least one Pauli check has detected an error. In other words, we measured non-zero syndrome on at least one check. State two means that we have zero syndrome on all checks, and there is no error in the payload circuit. And state three means that we have zero syndrome, but there is an error in the payload circuit. In other words, we have undetected error. But we may have a chance to detect this error later by the next Pauli checks. And we can calculate the probability to end up in each of these states, 1, 2, and 3. So we have this three-dimensional vector of probabilities. For example, if we consider just a payload circuit without any checks, the probability of detected error is 0 because there are no checks. The probability of no errors is 1 minus epsilon to the k, and k is the number of CNOTs in the payload circuit, and so on. And we model the application of Pauli checks by a Markov chain. So each time we apply a new Pauli check, the probability vector is updated by applying certain 3 by 3 matrix of transition probabilities. For example, if the chain visits state 1, detected error, it will remain in the state 1 because once an error has been detected, it remains detected forever. And if the chain visits state 3, undetected error, it can jump to state 1 with probability 1/2, because we pick Pauli checks at random, so the probability of detect any error is 50%. And if the chain visits state 2, no error, then it can jump to any other state with certain transition probabilities that depend on details of how we implement Pauli checks, what is our noise model, and so on. And we have calculated these transition probabilities for our noise model, and they depend only on error rate epsilon and Hamming weight of Pauli checks. But these details are not important. And now we can compute all quantities of interest. So we just take our initial probability vector, this one, and apply a product of 3 by 3 matrices. And we get the final probability vector after m Pauli checks. And by definition, post-selection succeeds if we observe zero syndrome on every check. And this happens if the Markov chain terminates in state 2 or state 3. So this is our post-selection probability. And logical error happens if the chain terminates in state 3, undetected error. And this happens with probability by 3, and we have to normalize it by post-selection probability. So our theory predicts that error mitigation based on Pauli checks works only if the error rate is below certain threshold value. And if error rate is below the threshold, the logical error probability decays is monotone decreasing as we add more Pauli checks. And if we are above the threshold, then logical error probability is monotone increasing. So error mitigation only makes things worse. And the threshold error rate can be found by solving this fixed point equation. And surprisingly, the error threshold depends only on the number of qubits in the payload circuit, but it does not depend on the number of gates. For example, a 50 qubit demonstration can be done with error rates below 1%. Even if the payload circuit contains a few thousand gates. Then another prediction of our theory is a logical error floor. So let's assume that the error rate epsilon is below the threshold. Then as we increase the number of Pauli checks, the logical error is monotone decreasing, but it will plateau at a certain non-zero value, which is proportional to epsilon times number of qubits. And this error flow originates from errors in the outer Pauli checks, which are undetectable. And here I show a comparison between numerical simulations and predictions of our Markov chain model. And here we look at randomly generated Clifford circuits on 50 qubits with 2000 CNOTs. Error rate is 0.1%. So if we don't do any error mitigation, the number of checks is 0. Then logical error probability is close to 100%. So the circuit output is complete garbage. But as we start adding Pauli checks, the logical error probability goes down and it saturates at a value about 8%. And you can also see that we have a very good agreement between numerics and our Markov chain model. And this plot shows the post-selection probability. If we don't do any error mitigation, then of course post-selection probability is 100%. And if we do, say, 10 Pauli checks, then we post-select this probability about 7%. Now, because Pauli check circuit is not fault tolerant in the usual sense, a single Pauli error can propagate badly and completely ruin the computation. And here I show example, then Pauli X error on the check qubit propagates to a high weight error on data qubits. And this error is undetectable because Hadamard maps X to Z. But we can detect this error if we add one extra flag qubit, as shown here. Now, if we propagate this Pauli X error to the right, it would generate a non-zero syndrome on the flag qubit. So such error is detected. And this plot shows logical error probability with and without flag qubits for the same payload circuit as before. And you can see that now we can reduce logical error probability from 100% to roughly 5 or even smaller percent. And we extended our Markov chain model to flagged circuits, and again there is a good agreement between numerics and the theory. Sorry. So far I assumed that we have all-to-all qubit connectivity, which may not be realistic. And we found that Pauli checks can be efficiently implemented even for the linear connectivity. And here I show a simple example when we have 2 Pauli checks on 4 data qubits. And this would be the naive implementation for all-to-all connectivity. And this is an equivalent circuit that we can realize for the linear connectivity. So you can see that we move check qubits are moved from the top to the bottom by applying these swap gates. And data qubits are moved in the opposite direction. And for any pair of check qubit and data qubit, there is some point when they become nearest neighbors. And at this point, we can implement a desired control Pauli operation by acting on nearest neighbor qubits. And we can reduce CNOT cost by observing that controlled Pauli followed by swap requires only 2 CNOT gates. So if we pick Pauli checks randomly, the average CNOT cost of implementing a single Pauli check for all-to-all connectivity and linear connectivity differ only by a factor of 3. So basically, this is the price we have to pay for the lack of connectivity. And if we come back to this 50-qubit payload circuit with 2000 CNOT gates, we can implement it for the linear qubit connectivity with 1 flag qubit per every check. And in this case, the logical error probability can be reduced from 100% to roughly 10%, which is not bad. But here, the agreement between the theory and numerics is much worse. And this is because Markov chain model does not work for this swapping network that introduces a lot of correlations between different checks. And next, we can simplify Pauli checks if the payload circuit is directly followed by measurement of all qubits. In this case, we only worry about Pauli X errors. So it makes sense to choose all Pauli checks on the right as Paulis of Z type. And once we have measured all qubits, Pauli checks on the right are equivalent to applying single qubit Pauli Z operation to check qubit. And we can use simple circuit identities to get an equivalent circuit, which I show here. You can see that now check qubit is measured before we start implementing a payload circuit. And this is good because check qubit does not have to wait and accumulate noise. Okay, so this is a nice theory, but does it actually work on hardware? And we performed the experiment on IBM quantum processor with 127 qubits. Here I provide a snapshot of device properties with the minimum, maximum, and average T1, T2, readout error, and CNOT fidelity. And here we only look at a subset of qubits which were selected for the experiment. And next, we need to choose some payload circuit. And our first payload circuit consists of repeated layers of CNOTs, as shown here. If you apply this circuit to the all zero basis vector, it does nothing because all control qubits are in the zero state. So we declare a logical error if at least one of the qubits is measured in 1. And of course, this circuit has no utility, but it is a good starting point. And these are the experimental data. So let's look at this green curve. And this would be the 6-qubit payload circuit that I showed on the previous slide. And the bold green curve is obtained by averaging over 10 random choices of Pauli checks. And those are shown by these light green curves. So in the absence of error mitigation, the number of Pauli checks is 0, and the logical probability would be close to maybe 90%. But as we keep adding Pauli checks, we can reduce logical error probability to roughly 20 or 15%. And for this experiment, we used one-sided Pauli checks because we measure all qubits at the end. And we used the network of swap gates that I showed you to implement everything for the linear connectivity. And here I show post-selection probability for the same experiment. So in the worst case, when we do 15 Pauli checks, we post-select only one shot out of 10,000 or 20,000 shots. Okay, and our second example is entanglement routing circuit shown here. So you can see that we create EPR pairs on nearest neighbor pairs of qubits, and then we apply a random qubit permutation that generates long-range entanglement. And this circuit is potentially more useful because entanglement is a useful resource, for example, in gate teleportation. And as before, we measure all qubits at the end. And in the absence of errors, if we measure EPR pair in the standard basis, we would get 0, 0 or 1, 1. And so we declare a logical error if we measure 0, 1 or 1, 0 on at least one EPR pair. And these are the experimental data. And here we observe an improvement from error mitigation, at least in some cases, like n equals 4, this orange line, and n equals 6. And you can disregard n equals 2 because in this case, the payload circuit is too small. And here I show the post-selection probability for the same experiment. And here it is slightly worse because we have to compile this random permutation of qubits into CNOT gates on nearest neighbor qubits. So the number of CNOTs is quite large. And to conclude, I showed you some ideas how to combine error correction and error mitigation. And one shortcoming of error correction is a large overhead of logical non-Clifford gates due to magic state distillation. And I showed you that this overhead can be avoided if we apply error mitigation at the logical level to realize logical key gates. In principle, we can reduce error mitigation overhead even further if we can do just a single round of magic state distillation. Then instead of say 10,000 logical T gates, we could possibly do about 1 million of logical T gates. And one shortcoming of error mitigation is its limited scope. It only works for expected values of observables. And I showed you that we can do error mitigation in a single shot fashion using Pauli checks. And we are optimistic that these Pauli checks can be implemented on perhaps 50 qubits if we have CNOT gates with error rate 0.1% or better. But of course, it's not clear what would be practical applications of such circuits that are close to Clifford circuits. And finally, I would like to thank my collaborators. So the work on logical T-gates is a joint project with Jay Gambetta, Christoph Pivot, David Sutter, and Kristen Tem. And Pauli check work is a collaboration with Ewout van den Berg. Ewout was the main driving force behind this project. And also Peter Georgievich, Dmitry Maslov, and Kristen. And with that, let me conclude. Thank you very much for attention, and sorry for my voice.